Christoph is a professor of building science at MIT, formerly at Harvard. He's also director of research at Solemna. He is an original developer of JSON at Reinhart in Canada. And probably also take it away.
Thank you, Jordi. This presentation is about the Lorax project, which I called that way because I read the book to my kids for the Has Fund at MIT, which is the arts fund. You always need something catchy so you get a memory competition. Which is about a multi-school, 20 schools of architecture involved effort to teach daylight simulations and to answering some fundamental research questions. And I'm just and I'm also showing you a continuation of our work trying to develop a series of exercises to teach daylight modeling. So generally, in terms of philosophy of how at MIT at least we teach simulations, is I have a whole class on daylighting modeling, and daylighting design. And then one on thermal simulation. And I think it's not really that much right now in my thinking that I break it up by first the daylighting and then the energy, but more by scale. I would say the daylighting class is turning ultimately more into a facade analysis class. According to the idea of what DIVA is about, it looks, of course, at the issues of daylighting and glare, but kind of at a one zone level, so at a facade type level. And then, of course, we have this new tool that we just released, which is kind of DIVA for the city. So this was the day on the Sustainable Design Lab when we actually released UMI. There's a software called Urban Modeling Interface, which, as I said, it's a DIVA for the city, which allows you to do all kinds of analysis for massing models of hundreds of buildings and so forth. And so actually the Sustainable Design Lab at MIT is, of course, there's overlap between Solemna and the lab. We look at design workflows, we try to validate them, optimize them, and our main focus areas are, not surprising, occupant comfort and energy use. So, it's interesting, a lot of you are using UDI and daylight availability. In a way, what I'm promoting in this class is to basically look at a space in terms of three components. And I promote looking at them separately in a way. So first looking at daylight availability. So when we look at a daylit space or the good facade, we want to see what are the times in the year when you actually have light within the space. That's one criteria. So do you have light, do you have not light? And then, of course, and that you saw in Alton's work presented earlier today, this idea of visual comfort. So we have light, how are people reacting to that? Let's look at that to a first degree separately. And then let's look at the energy use. Now, what's of course very important is that there are these interactions. You can't usually just look at one or the other. There's always this kit in between, and that's design and that is architecture. So what could that be, for example? So just different ways. The DIVA covers that to a certain degree, but that's of course the most difficult component when you come up with a very, very flexible design. When you have the European model, where people can switch off their lighting, actually imagine that. They can open their windows, they can change their Venetian blinds. It's extremely difficult and risky in a way, these designs, because you're not sure what's going to happen within the space. So we have these models, and Jeff is going to show some of them later, that are based on field studies trying to predict how people are going to interact with the space, but that's the most elusive, so to speak. And then, of course, also, that's a Swiss example, you have full automated control. So this is the Rolex Center by Sana, and there they have hundreds of these external Venetian blinds, and if you look here, here's the shadow at this moment when I took the picture, and each of these blinds automatically goes up and down exactly when the sun is shining on them and there's sufficient daylight. So that's a fully automated method. And then you have architectural control right here in New York, of course. I spent a day just to check it last summer in this space. It's extremely popular, the public library, and the sun really never makes it in. It shines on a few of these bookshelves for a few minutes in the day, but otherwise it's just the architecture that takes care of this control. And then you have, again, in Switzerland, the extreme of the adaptive control. I would say that's where a lot of the inspiration, at least for me, for the work that we talked about this morning came from. That the moment when you take away all furniture and give everybody only beanbags and they move around, then the idea of glare in a way disappears, because when you have glare, you just move somewhere else. So this is basically different ways of filling the gap between the daylight that I have and the comfort in between. But what I wanted to concentrate on today is really this project, this work that we're doing on daylight availability. That's the first step, how much light do I put in the space. I'm used to read that off. So what's really the relationship between the daylight that I have within the space and the building form, and how can I deal with? So just this part of the triangle. And that's a terribly cheesy graph, but that's really what it is. I mean, ultimately, initially, we're doing all the simulations because we want to separate our design, any design, into two areas. So we know, obviously, you don't need a simulation where the light comes in, but in a way, you know, there's a fall-up and there's one moment there you would say, okay, this is daylit, and then the rest is non-daylit. And when you want to evaluate somehow your design, you want to say, this is the daylit area, this is the non-daylit area, at a very, very basic level. So how do you do that? Well, first of all, we heard a lot about daylight autonomy, of course, today. So the problem is with electric lighting, something like this is very easy, because then you just take the illuminance meter, take some measurements, and you're done. And the moment when you switch to daylighting, then you see just here for a south-facing office, of course, the daylight moves back and forth throughout the day. It moves at noon back and forth throughout the space with the seasons. So this is why the idea, of course, years ago was say, okay, let's do a climate-based simulation. Let's model the daylighting for the whole year and say for every point within the space, how often am I beyond my minimum level? That's this idea of daylight autonomy. And finally, I mean, when we first came up with this, that was now 11, 12 years ago. Now it's finally in these IES and A daylighting metrics, so they basically tell you how to separate the space. And the way this is working is here you just plotted for the same space different daylight autonomy levels. So 90% daylight autonomy would mean that 90% of the time when somebody's there, you have enough daylight. Obviously, you can go lower and lower, and that number increases, or the area within the space increases. And so based on a study in 63 spaces, the IESMA said, well, a daylight autonomy for 300 lux, 50% of the time means it's a daylit space. So in practice, that would mean if you go in a space and just sit there with an illuminance meter, if half the time when you're sitting there you have more than 300 lux, you get an X and it's a daylit space. And then you move on and spend another year doing that. And of course, to save some time, you're using instead a computer to do that. So that's nice. The advantage of something like this, you can completely apply it to any project, to any design, because you have a very firm criteria. You need a form, you need a climate, and boom, you can do this very strong separation, which has a lot of value in itself. But, I mean, and here you just see how this looks, for example, in Seattle, Boston, and Phoenix. And often the surprise is that you don't get that different results. So first you make all this fuss that climate really matters, and then when we look at it in Seattle, Boston, and Phoenix, it doesn't matter that much. And the reason for this, we are just looking if we have enough daylight. We don't necessarily say, we don't penalize ourselves yet if we have too much. But for architecture, that's kind of nice, because it means that actually, well, first of all, the daylight availability is largely the question of the form that I have, the shape that I have, the window header that I change. All these things bring us more daylight. Of course, I have to do some follow-up studies in terms of energy and glare, because this one space might be okay in Seattle and not so much in Phoenix. But this is basically, since we're only looking at daylighting right now, this is what we get out of this. So that's in a way nice. There's a standard right now, so great work pays off. But I had this feeling that nobody had really tested this. I mean, we wrote these papers years ago, and after a lot of soul searching, the committee recommends it now, but we really wanted to test, well, how does this map to people going into spaces? That was really the idea. So this is really a little, I never have the slides usually with that much text, but this is really a student assignment that we did. And the idea of this is really that you do that at the very beginning of a class when the students don't know anything yet about lighting. And it's just this idea that I said, well, you walk in any space, and you, without having any background, you should be able to say, okay, this is the part that I think is daylit, and this is not. I mean, who's going to contradict you? And it's your impression. And so what we've done with this little exercise is we applied it first in Le Corbusier's Carpenter Center. That was my last year at Harvard. So we used it in the first, second floor studio space here. So this is how the space looks. The students got this assignment here. And in practice, that means they just got a floor plan. And they had to go in the space and basically draw. Here are the north windows. They had to draw where they think the daylight area ends, and they had to just pick some photometric values, so illuminance measurements, that they get a sense of this. So extremely simple exercise, and we consciously picked the space that actually is only partly daylit. I mean, it was very unlikely that anybody would think the very deep back of the space would be daylit, because otherwise the exercise is not so interesting. So this is what we got. This is one student, just that you get a sense of what the line would look like. And here you see the results from 2 classes. So obviously people don't have the same idea what means daylight. So it's all over the place here and here. But what we then did, we had a simple algorithm to basically extract how deep the daylighting goes. So this is the mean of all student evaluations. And if you overlay them, that is kind of interesting, you get something that is extremely close. So the typical idea always, a lot of people have different subjective idea. When you take an ensemble together, you get actually a reproducible line. And then we started to take this line and just compare it to our other metrics. So first we compared it to the 2% daylight factor. Worked okay at the side here, not so good here. We compared it then to the lead criteria, which has 250 lux at the time on different times in the day, 9 a.m. and 3 p.m. So one line fitted, the other line didn't fit. So I anyhow think this is a not very good criteria to begin with, and just that reflects this. Then useful daylight autonomy. So that's my issue with daylight autonomy. I know it's kind of handy to throw the energy of the daylight in one form, but it's not necessarily in a way that echoes what Max said. That's not how people think about light. If people don't know anything about light, they wouldn't say, oh, this is not daylight because there's too much daylight over there, and then draw a line like this. A line like this, people don't draw. They basically say everything is daylight until it gets too dark, effectively. And then in this first study, we were super happy, of course, because the daylight autonomy was very, very close to the ISNA metric. So that was good, which triggered a follow-up study, which we did, where we just said, okay, it's nice for a number n equals 1. That's not so good, so we basically wanted to expand the study. And the way we did this is what is in this Lorax project, and that is a collaboration with Tarek Bakar and with Dan Weissman, and who Tarek did really all the simulations, which was a huge amount of work. So what we did is we invited schools of architecture, and 20 said they would participate in repeating the same classroom exercises all over the world, really. And every study participant had to provide photos first of the spaces, a CAD model that was correct. That's probably the biggest problem, believe it or not, in a school of architecture. Student responses and optical material descriptions. So how did that work? So effectively, this is more a resource. This is a wonderful resource here, and definitely if you teach this, or even if you don't teach this, I would buy this guide. That's effectively, the guide teaches you a little bit about reflectances, but the great thing about it is there's this reflectance chart in there. So what you can do with it is this. So there are various ways, obviously, if we want to model the spaces, we need to know the physical properties of all the surfaces. So what you can do when you have a luminance meter, you can have somebody, in this case, Adam, taking a luminance meter measurement of a point, then you take an illuminance measurement at the point, and the ratio between the two times pi, that gives you the reflectance. So for a table like this, that's very basic physics, that would give you 57%. The disadvantage of this approach is most of you probably don't have a luminance meter because it costs $4,000. So instead, you can just, when you buy this guide that I just mentioned, you can use this normalized chart, and you can't photocopy it. I tried, that doesn't work, so you have to buy it. So what this actually does is really great. You basically pick the most similar color, and then see here the dot is brighter, here the dot is darker, and your eye is extremely good at finding basically this transition point, and then you just beat off the reflectance. And in this case, that gives you 54%, so you're extremely close or brownish. It works very well. So this is what we asked anybody in the study to do. Actually, if more for general interest, if you have this number, if you now want to make your own custom radiance material, if you want to know how to do it, then you can we have this little Excel sheet that you can download from our website. You'd use this chart for any surface that you have to determine the reflectance. Then you take just a photo of that material and put in the red, green, and blue color in this little Excel sheet, and here you spit out your radiance material. So that way, if you want to do something like this, you can do custom radiance materials for your whole scene. And this is, of course, Alton showed that this morning. If you want to, this costs $9,000. That way you can do a specular reflectance measurement, but that's probably not for everybody. So these are the schools that participated in our study, and mostly in the US. We have some in Brazil. We have actually 8 more schools that say they are going to present the results to us as well. So here you see some preliminary results. Actually, this is probably the most important slide, because here we said we want to interpret this result. So this is the old idea of saying, okay, if you have daylight autonomy open for more than 50% that are introduced before, and if 75% of participants say a spot is daylit, then we call it fully daylit. So if we pick any area here and we ask everybody in the room, if 3/4 of you independently say this is daylit, then we say this is daylit. And if it's between 1/4 and 3/4 say it, then it's somewhat daylit, you know. Yeah. And then if less than 1/4 agree, then we would say it's not daylit at all. It's kind of this correspondence that we want to generate. So basically for a fully daylit area, we say if you're over 300 lux, and for a partially daylit area, we use this 150 lux, and that works pretty well. So why we want to introduce the partially daylit area, because this idea of just, cutting one line through a building and says yes or no is very harsh, and it doesn't give you really a sense of transition. But when you use fully, partly, and non-daylit, you have more of you can draw that on any floor plan, you get more of a sense what goes on in the building. So this is basically what we're going to do for the spaces that you see in the following. So for example, here, this is a space at MIT where for the last daylighting class we did this. Actually, we did also some high dynamic range photography of the spaces. This is the space here under the MIT dome. And here you basically see the simulation and the student responses. So we're coloring the area according to our simulation. We can say what is daylit, partially daylit, non-daylit, and the same thing for the student responses. So you basically see that the general shape is very similar. You see slight divergences, but that's as close as we get with this metric. And if we loop now through several cases, here there's another space at MIT that we looked at, which is actually a pretty dark space, which you don't so much see in this image. And there we got very similar results. Here basically this is, we have 2 core daylit areas, and here you see basically the idea of this transition area emerging, and how similar it is in both cases actually. And here we have some more. This is actually University of Southern California, where they did it on the one cloudy day in the year. They managed to do this. And this is the space from outside. It's the space here. I haven't been there, so here's simulation and student responses. Similar shape. Light comes in from one side. This is University of Idaho. Very punch type window scenario again. Here's the space. This is how it looks. We got very good agreement. I rushed through them. This is Concordia in Canada, where they did an area for a high-rise building. The main reason why I find this is interesting, so here are the simulations, and here are the student responses, and here you basically see the responses are these corner. That's not something that we have here. And I think this really shows you where the whole idea of illuminance-based metrics collapses. Because in a way, this shouldn't work at all. I mean, everything what I'm doing here shouldn't work, because you can't see the light falling on a work plane. You see the surfaces behind it. So the less furniture you have within the space, the more unlikely this is to work. Because when somebody stands within the space here and looks at this wall, since the light comes from here, that's of course a lighting to a design trick. You can brighten up that wall. So this wall looks a lot brighter when people look at it, when the illuminance on the desk plane reveals. So that's where you start seeing these differences emerging, basically. And then similar here for a top-lit space at Miami University, which actually is in Ohio. Don't know that. Because you will see later why that's important. So that's a top-lit space. Top light coming in from here. A few more pictures of the space. Here's where you see it. Here it worked okay. It was actually not too much of a convincing result that we get in this space. Parsons here in New York, we did the same thing. the data space. Here it works pretty well. So this is actually a space that is our most problematic space. That's the extreme space. This is in Brazil, and a very sunny climate, obviously. And the main problem here is there's no furniture in this abstract space. So if we look here, what's going on, here you see it's this round building, very unusual. This is the simulation, and there are the responses. So the partially daylit area, that's pretty good, but the fully daylit area, they basically didn't find any agreement. This is the only area where everybody agrees that this is daylit, which is kind of interesting. So here, actually, this is more really for you, if you say, when you're in practice, should I use this metric or not? Here, basically, we summarize all the spaces. So what you see here is the percentage of the space that the simulation would say is partially and fully daylit. And here's the percentage of the daylit areas that the students say it's partially or fully daylit. So if our method was perfect, so basically everything would lie in the identical line. Of course, it's not going to happen. But when you look at this, it actually shows that with an exception of, this is in California, again, this is not Miami, this is actually Ohio. So with an exception of these spaces, and this is a top-lit space, this is actually pretty good. That means we can predict within 10% how much of a space is daylit. So if you're into kind of lead type analysis, or if you want to tell your client this is how much of your area is daylit, that's actually extremely precise, given that these are people, and we heard this morning, some people are never satisfied. So based on this, I would actually say I would recommend using this type of metric for the spaces. It's kind of the gist of the study so far. So this is the Lorax project, just looking at the time. This is something that basically is a continuation of some earlier work that we've done. So the Lorax project was really about, practically, if you use this new daylight autonomy metric from the IESNA, so 300 lux occupancy from 8 a.m. to 6 p.m., which is the default for DIVA. If more than 50% is your daylight autonomy value, you can call this a daylit area. And this is, of course, what the DIVA report shows you. It tells you what's the percentage of the area of all of your grid points that are daylit or not. So this is now more about, well, how should we teach simulations to students? Or if you have somebody in your firm that has never done a daylight simulation, how should I best do that? And the first two slides, these are old slides. So the first time we did this, I taught Ecotect, and at the time I thought in 2005 one could not possibly get that wrong, right? Ecotect was drawing a box. Andrew Marsh could do that in 30 seconds for you. So you think everybody does that. And in that study, we had this corner room, a grid room. This is the best practice model. And the exercise was just model the mean daylit factor at this time in the space. And what we basically got was, well, we started, that's Diego Ibarra's thesis, we started identifying what people do wrong. Well, the first thing is they don't model the space. This doesn't really look like this. So that obviously doesn't work. Then, of course, there's the way bigger issue of software interoperability. So in this case, they used another software, exported everything in Ecotect, and all the trees for construction line. These are things that in practice, of course, you encounter all the time, that transitions between softwares don't work very well, generally. Or they didn't set the materials right. So based on this old study, basically, we identified, by going through all these files, typical mistakes that are being made. And this is actually, that was the summary of our study. So in the first year and the second year, this would have been an acceptable mean daylight factor, and this is what everybody got. So obviously, in both cases, I'm not a great educator. What we did then, we had this list of simulation tips. And these are part of what we basically right now give to our simulation novices. So first of all, more of a general idea, what kind of tool should you use, what are you after to model. Then you can download that as well from our website. Then more the practical things. When you model the daylight within the space, you need a ground plane. You need to consider the thickness of walls. It's very practical thing. And then how do you set up your simulation? And now we wanted to see, does that lead to better results? So in the last MIT daylighting class, this is all the assignments that we did throughout the term. And this is basically the ones in orange are the ones that count more. So the first week I typically do an essay on daylighting. What do you think of daylighting? What is good, what's bad, what matters for you? This is basically this daylit area study where you walk within the space and draw the line. But at the same time, I asked the students then to look at the time and what time they're in the space, to measure the illuminances along the central line, and to take a high dynamic range photograph, so a calibrated photo of their space. And then they have to model that space at the moment when they were in this classroom. And that's, of course, ideal, because that's a point of reference between reality and simulation. And then we have to work through the process of looking where the model went wrong. But they know what the right result is, and they have to basically work towards this. And then so this is this assignment here. Then it's more that they are allowed to play around with. So in this case, they could play around with shader rate and come up with a shading system for the space. Do a simulation study. That's, of course, very important if you haven't done it, that you just understand the simulation parameters. What does an ambient bound and an ambient division mean? That you just apply that to some spaces. And then at this point, I had to do the daylight availability max, so daylight autonomy and so forth. And just the results, and then they did some glare analysis and electric lighting analysis. But what we got, again, for this space here, for our best practice model here, their results were considerably better than in the first year. So this is the mean illuminance, and these were measured illuminance, and these were basically all the student simulations. So they were converging, really, of all their models, what they got. And actually, when we looked at the comparison, so in dark gray and black, that was the distribution of errors that we had in the previous classes. So this time there's a singularity. I mean, they're overestimating by 50%. But what's 50% among friends? At least they're in the right ballpark. And we still probably have to understand what really goes on here. I actually think the glazing that we have, nearly everybody is too rushed to model the glazing properly. So they just pick one of the default glazings in DIVA, and the default glazing was too high compared to what they had in reality. So I think that goes on here. And that's pretty understandable, because it's not that easy to model a glazing properly in DIVA. So yeah, just in the interest of time, I actually had some rules of thumb, but I don't have time to talk about that today. So I guess I leave that out. Any question?
Right. One question, please.
Yeah.
So, because there's a lot of discussion, to go back to the part where you're talking about the previous, the Lorax project, where you're doing the illuminance studies and correlating them with the simulations, and you said it shouldn't work, because you're looking at illuminance data, not luminance data. So, but it seems to work. So, do you have a hypothesis for why it is why it does work so well?
Well, I mean, it's kind of course, provocative to say it shouldn't work at all. I mean, there's some hope and expectation that it would work. I think where it doesn't work, it's typically the effect that it's a luminance-based intervention that you look. So in the space where it doesn't work well at all, this is a space where I think this concept of a work plane is lost a bit, because there's no work plane here. They're not even tables. In the other spaces, there were classrooms, and of course, the moment you have a classroom and you actually have a desk there, then the work plane illuminance is a reality, more or less. It's not what they see, but it's still, there's some reference point. Here, I think this is not the case anymore. They basically see the back wall that's dark and the floor that's white, so they think everything towards the wall is black. I think that's where are cases where we shouldn't be surprised if it doesn't work. And on the positive side, when you look at this here, actually, if you have typical classrooms or libraries or spaces when this reference surface has some sense, it works quite well. So ultimately, I would say it works. I would have thought, in a way, it surprises myself. I think it would have been worse than it is.
Well, it seems like even at the Valix conference and some other places, people are talking about using luminance as a better measure of visual comfort and all these things. So, I mean, I think it's pretty interesting that, there's some talk about not using illuminance as much to determine how well daylit a space is, but this would seem to contradict that.
Well, when you just want to know, of course, we picked you got the difficult one this morning with Alston, and I picked the low-hanging fruit here with illuminances. That works pretty well. So if you buy into this concept of, say, we want to first look how much light do I have, and then I want to look at visual comfort separately, and then we're going to put it together, then just looking at do I have sufficient light, that works. And this confirms actually that daylight availability and useful daylight illuminance. I'm moving a little bit away from that. I see the benefit for design because of you can kill two birds with one stone. Obviously not my mother tongue. But if you want to kill birds with two of them with one stone, then that's a good... that gives you some idea, but I don't think it corresponds to how people experience space. You, in a way, have to buy into that when you have people that are not advanced as you. They are kind of bewildered by the fact, obviously, that there's no light near the window, seemingly, or that you don't score high near a window.
Was the exercise done just once? I mean, was it an instantaneous exercise, or did they go back to the space and redo the line based on?
They only do it once. What was interesting for me, and this is of course something that we can tinker with, the first study that I showed you, where we did that in 2 classes, where I showed you ultimately that the results were very similar. This was done 2 months apart. Different sky conditions. So this one here. Too many slides. Here. So this and this. This was a class in the spring. There was snow on the ground, and I forgot in one. Here it was sunny, and here it was very dingy and cloudy. So it's very surprising actually that the results here. That is really surprising that they're that close. Which I think is because. There again, I would say the illuminance, the absolute numbers don't really work. People go in a space, adjust to the lighting level, and then it's a matter of relative proportions of light. Has to be, because it was so much darker here than here. Yeah, Joe?
I was just curious on the Brazil data was quite a bit different. And I noticed in the images it seemed like there was a considerable amount of glossy glare on the ceiling. Do you think that could have had some impact on the perception?
Well, I mean, to be honest, that was a model that we sent back 5 times. And without so we sent back the models and only then looked at the user assessments. Not that we sent back models that we didn't like the results. No, but we sent back because it didn't match with the pictures. At first, the building was round and the model wasn't round, so that was really odd. No, it was really so.
So your error bars on that Brazil one.
Well, but I mean, I can't say that. I mean, but we basically went back and said, basically, what's the material properties? Did you check carefully? Can I get another round of photos? Because that's the most difficult part ultimately here. It's easier when you have one. We had one person. Bless his soul, Tarek, who did all the simulations, that at least there's consistency there. But he didn't go to Brazil, right? So that is just something. The glossy surface might have mattered to that. I think the Brazil space, it's good to have in because it's just it's an uncommon space, right? It's just, I don't know what they use it for.
And then for the sky simulations, how did they correlate that?
Well, they didn't. I mean, it's a climate-based metric. We take the climate file for Brazil and run it through the whole year. We don't look at their particular moment in time. So interesting it is, I always wrote that, I'm not sure if you saw that, what the sky condition was. It's usually that the instructors give people a 3-hour window, 2-hour window to do the analysis, to walk in that space and draw the line. And the sky condition changed. So it wasn't that in all the cases it was cloudy or sunny or something like this.
Is there any sort of connection between the extreme outliers being all on cloudy days or all on sunny days?
No, it wasn't. I mean, the one thing, that's why I'm joking, it's the one cloudy day in LA that they picked at USC. But that's a small. I don't know. It doesn't necessarily mean that they have space. It's not a really bad space if you look at it. I mean, in terms of when you look at the statistics, it looks far out there, but the pattern is the same. It's just a sided space where the light moves in and then moves a little further in. Yes.
It's interesting that, like, in a lot of the presentations today, a lot of presentations focused on this UDI overexposure instead of using the light switch algorithm and modeling blind operation.
Yeah. So
what would that percentage of DA of acceptability be using light switch? Like, would it be 30%? Would that would shift from the 50?
Well, that's of course, I mean, practically I'm convinced that it's not being done because the radiation maps are super fast, right? That daylight autonomy is not super fast, but it's not super slow. And then when you come to snapshot and point glare, that's still okay. I mean, annual glare maps, give me a break, that takes a long time. You have to be a researcher to do this right now. So I think one of our main focuses right now is how do we get this whole thing really fast. And I think that's what it is. If you were to put in a blind system, that would of course reduce the results as well. But it's actually also
that's
interesting.
Coming from me in SOM where we like to overexpose our spaces.
Well, but you can just use energy to basically fight back. You have daylight. You have wonderfully daylit spaces, right? I mean,
They're wonderful.
No, what you have to do, I think then I would use the dynamic shading system. Because of course, when you have a too big window and you put a shading device in, then the shading device is always down. There was really this aha at the last Diva Day when Carlos and Amaya and forgot her name. When they model the space with skylights in the Harvard Library, and then they put in movable louvering system in the skylight, and then they ran the simulation, and they found out that the louvers were closed the whole year. That's a super strong argument, I think, for a designer, because that really means, well, that obviously doesn't work. That can't be my design intention. And so once we do that more fluently, then I think we get away from the big... If they believe Diva, then they get away from the big spaces, from the big windows. Any?
Thank you for that.